Hello, I'm Ho-Young Lee from Seoul National University. I present our paper with title Optimal Estimation and Feedforward Control of Strip Longitudinal Hardness for Thickness Hunting Suppression of Tandem Cold Mill Process. Contents of the presentation is as follows. First, I will introduce the problem we solved and why this is important and challenging problem. Next, I will present how we addressed the problem. Summary of what we did will be given first. And then, Tandem Cold Mill process model will be given as background for this research. Next, concept of strip longitudinal hardness parameter will be introduced, and detailed feature of a hardness estimator framework and hardness feedforward controller will be explained with their simulation results. Finally, we will summarize our contributions and conclude the presentation with our future plan. Tandem cold mill process, which is shown as the figure, produces hot rolled steel into cold rolled steel. However, from the non-uniform hardness of hot rolled steel, thickness hunting is occurred. Here, thickness hunting means fluctuation of thickness of cold rolled steel, which can deteriorate the product quality and directly affect the profit. Therefore, thickness hunting suppression is an important problem. To suppress the thickness hunting, we need thickness controller considering non-uniform hardness. But hardness is hardly measurable feature, and OEM, original equipment manufacturing controllers, do not directly consider the effect of bearing hardness. Therefore, we want to estimate hardness and use it to suppress the thickness. But this is a challenging problem because TCM is highly nonlinear system and rolling stands are interconnected to each other. Also, sensors are sparsely attached as shown in the figure, which means we can only measure information of certain points. To solve this problem, we adopt the concept of a strip longitudinal hardness parameter, which means if we divide the strip longitudinally, each segment has different metallurgical characteristics. Then we enhanced our TCM process model incorporating this concept of strip longitudinal hardness. Next, we designed hardness estimation framework, composed of two complementary loops. One loop uses optimal sensor fusion, utilizing redundant information, and the other loop uses nonlinear optimization, utilizing massive data from TCM process. Then we design hardness feedforward controller that controls delivery thickness under varying hardness. Finally, using our pre-developed physics-based TCM simulator, we validated that our proposed estimator and controller are able to suppress the thickness hunting as shown in the figure. Now, I will briefly introduce TCM process model as background of this research. TCM is composed of several rolling stands. At each stand, highly nonlinear rolling phenomenon is occurred. The rolling can be simply expressed as the two representative equations inside the blue box, but many other equations in gray box are omitted in these equations. Besides the rolling equations, we have two equations for the single stand. This is empirical relation between thickness and roll gap, and this is equation about in and out mass flow conservation. Because the adjacent rolling stands are connected with strip, there are relations from this interconnection nature of TCM. With the assumption of fast propagating tension stress on the strip, tension stress between two stands are homogeneous. Also, from the strain-stress relation, we can get tension-stress dynamics by differentiating the relation. Note that tension dynamics are affected not only by variables of stand itself, but also by variable of next stand. Therefore, TCM is not a cascade but complex system. Because the strip is transported from former stand to next stand, entry thickness is actually delivery thickness of the former stand before certain time delay. Now, let me explain more detail about the concept of a strip longitudinal hardness parameter. Generally, we can assume that each segment of a strip has different metallurgical parameters which affect hardness of the strip. For the simplicity, we choose alpha as representative hardness parameter that represent hardness of the strip segment. We chose alpha because it is directly proportional to deformation resistance K bar, which is kind of hardness during rolling, and alpha also amplifies the effect of the term R bar plus beta to the power of gamma, which includes thickness reduction R bar. From now on, we will treat the other metallurgical parameters, beta, gamma, A, as constants. Applying this strip longitudinal hardness parameter to TCM process model, we have transportation relation of representative hardness parameter alpha and annealed thickness HA. Then we can enhance TCM process model as figured in right bottom. With this TCM process model, estimation framework for real-time and online estimation of the representative hardness parameter alpha is designed. The estimator is composed of two loops. The first loop is to estimate variables we cannot directly measure due to the lack of sensors or sensor arrangement. Using probabilistic approach, distribution of estimation variables are obtained with optimal sensor fusion, utilizing redundant information. Because this loop needs to estimate variables and need less computation, it runs fast, actually every time step. The second loop is to estimate unknown constants, including metallurgical constants and friction model constants, because this loop uses nonlinear optimization utilizing massive data from the TCM process. Enough data accumulation is needed for accurate estimation. Therefore, it runs slow once in few seconds. These loops are complementary because each loop needs result from the other loop for calculation. Now let me explain more detail about the first loop, estimator of variables. To utilize probabilistic approach, we assume that every variables are random variables with normal distributions. Then, from the distributions of measurement data and through the TCM process model, we can obtain normal distributions of the unmeasurable variables. For example, we can get distributions of delivery thickness from linear combination of two distributions of S and P, which is measurement data. For the nonlinear combination of random variables, we use the unsentient transform to calculate the distribution. We also get distributions through transportation as in the bottom blue box. Note that this calculation is only possible with estimation result of the other loop. Among the normal distributions we get, there are redundant information. It is well known that we can combine two probability distributions from different sources and get more accurate distribution. Simple example is shown in right top graph. We can see that distribution of x from measurement A and measurement B is combined to more sharp distribution, which means combined distribution is more accurate. Utilizing this optimal sensor fusion, our delivery thickness distributions from two different equations can be combined into more accurate distribution of thickness. Also, our representative hardness parameter distributions from three different sources, rolling equations, transportation, and material continuity assumption, can be combined into more accurate one. In the second loop, we want to find the unknown process parameters, which are constants, satisfying the rolling equations in middle blue box. Then we can design nonlinear optimization problem, as in the right bottom box. It computes the measured rolling force P and exit strip speed Vf with calculated ones through rolling equations. Because the accuracy of this optimization depends on the amount of the data, we need to wait for enough data accumulation first. With enough data, we can start estimation using data bunch in a manner of moving horizon. Note that this optimization needs estimation result from the first loop. Also note that this loop is also online, same as the first loop. To validate our estimation framework, we tested our result to pre-develop the physics-based TCM simulator. We gave the simulator ground truth hardness parameters and run with our estimation framework. Then we can get accurate estimation of representative hardness parameter. We can see root mean square error of the estimation from the table, which are near or under 2%. Note that RMSE tends to decrease for lateral stand, because the lateral stand succeeds estimation result from the former stand and uses it to optimal sensor fusion. Therefore, for the lateral stand, variance of the hardness parameter distribution becomes small. Variance graph of right also shows this tendency. The plots for the estimation result are shown in bottom. Left bottom graph compares the ground truth and estimated hardness parameter for whole TCM process. Right bottom graph is zoomed version of the left one, where the zoomed region has large thickness hunting. Pattern of varying hardness is important for further control, and we can check that estimated hardness follows the hardness varying pattern of ground truth very well. The OEM, original equipment manufacturing controller, is composed of numerous control units, as shown in this simulation figure. It is too dangerous to change whole controller of the plant to newly developed controller. To simply and safely apply the controller to the plant, we design Retrofit controller, which respects structure of the OEM controller. In other words, we design hardness feedforward control unit that can replace OEM feedforward control unit without changing other OEM control units. To consider varying hardness, we incorporate representative hardness parameter into the derivation step of OEM feedforward controller. Then we could derive enhanced version of feedforward controller that not only considers varying entry thickness, but also varying hardness. To validate our controller, we apply the controller to our aforementioned pre-developed TCM simulator. The proposed hardness feedforward controller is applied to the fifth stand because estimation variance is minimized at the fifth stand. Then we compare the result with the case of OEM thickness feedforward controller. From the graph, we can see that thickness hunting is well suppressed compared to the case of OEM controller. From the left bottom table, we can see root mean square error of the thickness. Using our controller, the error is reduced by 37% compared to the OEM controller. Another feature for the evaluation is off gauge. It is length ratio of strip exceeds given thickness error tolerance, which is directly related to the profit. From right bottom table, we can see off gauges for 3 different tolerance criteria. We can see that our proposed controller reduces the off gauge compared to the OEM controller. Especially, we can observe drastic reduction of off gauge for the tolerance ±2% and ±3% case. This is the conclusion of the presentation. Our contributions are as follows. First, we adopt concept of a strip-longitudinal hardness parameter. Secondly, we propose real-time and online estimation framework for hardness, which is hardly measurable but important feature. Thirdly, we proposed Retrofit hardness feedforward controller to suppress thickness hunting under varying hardness. Last, we utilized interconnected nature and sensing sparsity of TCM process for our framework. Our future plan is to apply the proposed estimator and controller to real plant for further validation. Thank you for listening.